Hi, I'm Abraham Gale, a PhD student at Rutgers University, and this is my work with my advisor, Amelie Marian, on explaining monotonic ranking functions. Many important algorithmic decisions are made every day by non-experts. That is to say, people who do know a lot about the specific subject matter of the decision, but do not have expertise in designing the ranking function, which is actually used to make that decision. Some examples of this are school admissions, sporting event decisions, job applications, and organ donations. For example, a school admissions officer might know what kind of student they're interested in, but not how to design a ranking function that will bring that kind of student to the top of the rankings. Sporting event decision maker might know what kind of athlete they want to win the gold medal, but not know how to bring that kind of athlete to the top of the rankings. And so on for all the other applications. So the goal of this paper is to define metrics which help these people bridge the gap between their domain expertise and their lack of statistical expertise, and to allow them to design functions which correctly and successfully accomplish their goals. So we have three families of metrics we introduced in this paper. First, we have ones which measure the contribution of each parameter to the final decision. And we're going to focus on one of them in this presentation for time reasons, such as participation. We also have metrics that measure the similarity of selected objects to each other, which is we call diversity. This is not the same as how representative the selected objects are of the distribution as a whole, which we call disparity, even though these are conflated in some previous work. And we're going to go into more detail about disparity later in the presentation as well. At first, you might think in a simple function, such as a weighted sum function, that equal weighted parameters will have equal weight in deciding the final outcome. But that's not quite the case. The distributions can get involved as well. For example, these two parameters have this, if you give them the same weight, it's obvious parameter 2 will be more important because essentially we've applied the weight into the distribution. So we see here that you have to actually pay attention to distribution and have a way of summarizing that to tell you whether your weights are actually accomplishing what you think they are accomplishing. To start, before we get started with this, we'll need a concept of a threshold, which for monotonic ranking functions is the point after which you accept all objects. And here are three different pairs of distributions with three different thresholds. First one is two normal distributions, where we see the threshold is quite high because they're end weighted. This is one normal and one uniform. And this is two different normal distributions. And in this case, the threshold is lowest and it goes on this way. So in order to capture this idea of how much the distribution affects the decision, we have a metric called participation, where if you look at these regions, we see the green region have objects that are highly weighted in both. Blue region is only highly weighted in the normal distribution, and yellow region is only highly weighted in the uniform distribution. And we see there are a lot more points in the yellow box than in the blue box, and therefore the yellow or uniform will have a higher participation because it more often participates in the ranking decision than the blue box. Let's look at applying this to a specific instance. So in the Decathlon, the designers of the function wanted a function which would select the best overall athlete in 10 decathlon events, and they wanted each event to have the same importance. This isn't very straightforward since the events are fundamentally incomparable. 1500 meter dash is time, long jump is distance, high jump is height, and even among ones that have the same general unit, like 400 meter and 1500 meter, it's not obvious how to convert under 1 second the 400 meter to 1 second in the 1500 meter. The traditional function uses 1,000 points per event based on the idea of 1,000 points being a world record performance. It was designed in 1984, so obviously it's no longer the case, but that was the original design. In the final score, we add up all the points equally to get a final score. If we apply our participation metric here to all the decathlon data, we see that it doesn't do a very good job of equating. We have 5 events here which have pretty equal weights, at least relatively equal, and that's the 100 meter hurdle, long jump, 400 meter, and 100 meter dash. And these are all pretty good. But then as we go down the list, we see some events that participate hardly at all. When we get down to the 1500 meter dash, the scores here are so low, they hardly ever participate in the ranking decision. And if we can use something like this to see how we might want to redesign the function, maybe give a little more weight to scores in 1500 meter dash, maybe a little less weight to some of the other ones. And therefore you can use this to make the decision that you have in your head and try to actualize it into a real function. So a lot of times users care not only about how how much each parameter participates, but also about how different selected objects are from unselected objects. For example, in a school decision, you might want a representative set of selected objects in low income, race, and gender, none of which go directly into the decision-making process, but you might still be interested in how different they are from your selected and unselected objects. So we designed a metric called disparity to measure this, which is it's the vector difference between the average object in the two sets. And we can mix discrete and continuous parameters, and it's also relatively human interpretable, meaning that in machine interpretable metrics, you want it to diverge quickly. If there's some disparity, you want to quickly have a very different score disparity, so that you know that if it's a little bit too much, then you will quickly see that. Where human readable metrics, you want twice as much disparity to have some meaning. It will mean that it's twice as bad in some sense. So in our case, twice as many disparity means twice as many objects are impacted. And here's a visualization to kind of understand what disparity is. So the gray points represent the unselected objects. The red points are selected objects. The black cross is the average of the gray points. Blue cross is the average of the red points. And the disparity is the vector between the black and the blue cross. And we can take the norm to get a general idea, or we can just look at the whole vector to know how different it is on each direction. And if we apply this back to our original decathlon case, we can see something about the decathlon data set. So here's a graph of what continent winners come from and how old they are in disparity, none of which go directly into the decathlon function, but all of which are interesting. And we might want to know how well it does. And we see that Europeans are selected and do much better over pretty much all Ks than the people from other continents, and North Americans do somewhat worse. And those are the main contributors to disparity. Age is a minor contributor, older is slightly better. Possibly, you could speculate as to why. It might be because younger athletes who do badly don't compete again. Could be because only world-class athletes compete later in life. Could be any number of reasons. And other things have pretty minimal disparity. There aren't that Asian athletes pretty much the same, whether you're selected or not. The continent doesn't really tell us much about that. And so we see from here, if you wanted to make the function more fair across continents, you would say, we need to represent Europe a little less, and you could try to find a way to do that, now that we understand our function better with the help of the disparity. In conclusion, our paper does a few things. First of all, we want to just express the idea that knowing the function doesn't actually tell you how objects are selected. You need to also pay attention to underlying distributions. We propose a family of metrics to help decision makers, even ones with very minimal statistical education, understand the behavior of their making functions and adapt their choices accordingly. And we validate our metrics using real data from both Decathlon and New York City school admissions. In the future work that we're currently working on now is we want interactive interfaces so people can directly use this. And we're also looking at some compensatory techniques to mitigate bias. And if you have any questions, you should feel free to email either of us, which email addresses are here and on the paper. And that's all I have. Thanks.